Good morning. I wanted to take a step back before we proceeded. I'm just going to show you the solution to one of the questions in review 7.1. But just to kind of do the step back, this we looked at last day, that really this is represents a beam of electrons, and it's passing through if the beam of electrons was left to its own devices, it followed the dotted line. But there is a deflecting plates here, and activation of these plates, passing a current through them, will cause them to deflect. This is nothing new. We've looked at the cathode ray tube before. Okay, so what this means here, this V here, I'm just going to color code this, represents the velocity of the particle. So this is the velocity particle. This length here is here. This is the so this is the distance to the screen. Basically, the screen being the end of the cathode ray tube. This here, this is the mass of the particle. And so that would be standard. If it was an electron, it's 9.1 times 10 to the negative 31 kilograms. If it's what do you call it, a proton or a neutron, for example, it's going to be higher than that. It's 1.6 times 10 to something kilograms. I can't remember. Anyway, the only other thing that I wanted to point out was that this Z in the textbook doesn't use Z for the deflection. They use Y. So this Z here is the deflection in either direction, and this the textbook uses Y here. Okay, so that was just wanted to step back. So at the bottom of the page, you'll see at the bottom of the page, continuing on to the next, there's a statement that goes like, it says, for the most part, problems centering around this topic are not multi-bit variable calculations. In other words, you don't have to find a whole bunch of, they don't give you a whole bunch of data and then you plug them in. In the most part, it's just comparing things, okay? So if all things are held equal. And so that's where this question comes in that we dealt with, or that we wanted to deal with. And that is on which page? Just a minute, I just got to sort this paper out. 7.1.1. It's back here. Getting close. Okay, this is question number 9 on page 273, and it says, when the solenoid current in an electromagnetic in the arrangement used in investigation 7.1.1 is 2.2 amps. The beam of the CRT is deflected 1.2 centimeters. What will the deflection be if the solenoid current is increased by 3.6 amps? Well, we didn't do 7.1.1, but the equation that it's referring to is this one here, is the one that we just looked at. Okay? Papers, papers, papers. That is this one here. Okay? Now, the thing you have to wrap your brain around, and this may not be intuitive to you right away, is that the deflection, it depends on how much current you're running. And so what they've said is that they've given you a scene. The scene 1, which is referring back to 7.1.1, they say in scene 1, the current is equal to 2.2 amps. Okay? And so the deflection is Y is equal to 1.2 centimeters. In scene 2, I is equal to 3.6. Maybe what I should do is just to keep this understandable, because we're running into a lot of similar variables. So if this is, say, I1 and this is Y1, this is I2 and this is Y2, what we're trying to, this is a simple ratio. Intuitively, as I mentioned, the greater the current, the greater the deflection, right? And it should be proportional. So really, the way to set this up is to set it up as a proportionality, where Y1 over I1 is going to equal Y2 over I2. And so if you do that, you end up with this. You end up with 1.2 centimeters goes to 2.2 amps as X centimeters goes to 3.6 amps. And so if I 3.6 times 1.2 divided by 2.2 comes out to 1.96 centimeters. Okay, so reality is that you won't see it reported as 1.96 because these only have two significant figures. So this will be reported as 2.0 centimeters. Now that should make sense. It should, the proportionality, if you think about it, it will make sense in the long run. Okay? Okay, we want to move ahead, but I got to clean up my desk here. So let's put this paper away. And we want to look at done with that page. Okay, so this is page 4, right? Again, I get the color paper. So sad, so sad. Okay, so what this is magnetic field strength, B, calculating magnetic field strength. Okay, so what this is talking about is if you have a magnetic field. So here's north, and here is, say, south. And so the magnetic field goes from north to south. So I'm just going to worry about the magnetic field between the two, directly between the two poles. I'm not going to worry about the other ones. So the idea here is if you've got a particle that is moving like this, perpendicular to the field, what is the force on it? And so the force, and this is one of those things you want to write down on your card, and write it down under calculating or magnetic field strength. Okay. The magnetic force on this, so the force acting on this this particle, okay, is going to equal the charge on it times the speed or the velocity of it times how strong this field is between. So we have a weak field, your force is going to be smaller. If you're traveling, if you're having less charge on it, it's going to be smaller. If the velocity is smaller, everything's going to be smaller. Okay, so excuse me, I got something in my eye. So in this equation, units of measurement for the force, of course, is always newtons. Charge is always measured in coulombs. The velocity is in meters per second, and the field strength is in Tesla. So if you wanted to determine what is the unit, what is a Tesla, this is what it is. It's a 1 Newton per Coulomb meter per second. Okay, or if you wanted to translate this, it end up to be Newton seconds per Coulomb meter. If you wanted to do that, but I'm fine with it as it is. Now, normally in the textbook you won't see it written in this order. You'll see it written as force is equal to B. They usually put the B first, the field strength first, charge, and then the velocity. Now notice that these three are all vector quantities. Okay, so that means that if you have this whole thing at an angle, if the particle is moving at an angle, okay, then then you have to invoke the sign to say what is the directionality. Okay, so or not directionality. Well, I guess you could be asked to solve for directionality, solve for theta, but the force is going to be affected by the angle of the wire. Okay, or not the wire, the particle moving through it. We'll talk about wires later. Okay, so again, this is simply plug and play. Let's look at a quick check, do a quick check problem, just to show you how simple this is. You may recall that I've often referred to this as a simple plug and play course. So I'm looking on page 275, and the question says, I'll throw it up here so you don't have to turn your. So this is what it says: an electron traveling with the speed of 2.0 meter times 10 to the 6 meters per second moves in the direction perpendicular. Okay, so we're good. We don't have to use sign. To a magnetic field of strength 2.5 times 10 to the negative 2 Tesla. Okay, So we know that this is going to be, this is V, this is B, okay? Electron also tells us what the charge is, okay? So let's write all that kind of stuff down. Put that back in my binder. Very good. So this is the charge on an electron is 1.60 times 10 to the minus 19 coulombs. Okay, that's by definition. The velocity that we're given is equal to 2.0 times 10 to the 6 meters per second. The magnetic field strength perpendicular is 2.5 times 10 to the negative 2 Tesla. This is broken up into two parts. They're asking first for the force. How do they say it? The force acting on the electron. Well, the force acting on an electron is equal to B Q V. Okay? And so this is, I'm not going to put in the units, okay, because I've got limited space, as you can tell. So this is 2.5 times 10 to the negative 2. That's in Tesla, of course. This is charge 1.6 times 10 to the minus 19. And then the velocity is equal to 2.0 times 10 to 6 meters per second. Run that through your calculator and it comes out to 8.0 times 10 to the minus 15 newtons. Okay, so that's A. That's the force. That's the force. The next part is asking basically what's the acceleration? B. What's acceleration? So we know that force is equal to mass times acceleration. We have just calculated the force. So this is going to be this value. The mass of the electron is a what do you call it? A constant. 9.3 or 9.1. I can't remember. 9.1 times 10 to the negative 31. So let's just continue this. This is, first of all, let's rearrange this to find the, to solve for acceleration. So acceleration, therefore, is equal to force divided by mass. And the force is equal to 8.0 times 10 to the negative 15 newtons. And I'm going to divide that by the mass, 9.1 times 10 to the negative 31 kilograms. And so the force acting on that electron, or no, I'm sorry, the acceleration is 8.8 times 10 to the 15 meters per second squared. And it says what's the orientation? It's perpendicular. It's already told us perpendicular. Or no, the force. This is the right-hand rule. So this is going to be upward. So it's going to be perpendicular to, how do I say this? It's going to be perpendicular to the trajectory of the particle rule. So what that means is that what I mean by that is, suppose you had this situation here, where this is north, this is south, and the particle is going this way. Okay, so you point the thumb of your right hand in the direction, with your fingers pointing in the direction. Okay, thumb pointing the direction of the particle, fingers pointing the direction of the magnetic force, and the palm of your hand in the direction of the force. Okay. No, what they're doing? No. I'm wrong here. It's just perpendicular to, not the trajectory. It's just perpendicular to B. Perpendicular to B. I'm thinking of the force. This force is pushing down on this. That's what's happening here, using the right hand rule. Sorry about that. I was confusing you, confusing me. Okay, so the force is actually, if the axis for the direction of this, it's going to be in downward direction relative to this. If we were to flip these, it would be in the upward direction. The acceleration is equal to the trajectory. Okay, I'm done with that one. I encourage you guys to practice those. You find that if you practice those easy ones, then when you get to the more difficult ones in the unit reviews, then those make more sense. Okay, so that is that. Goes back there. This goes over here, and so now we want to take a quick look at solenoids, and yeah. So we want to look at magnetic field within a solenoid, and I'm not going to spend a lot of time in this. What I'd like you to do is I'd like you to ignore these equations here, because the textbook uses a different format, and using this leads to more calculations, I think. So I'm going to ask you to just get rid of this. Okay, just get rid of this. And at the same time, I want you to do two other things here. I'm going to get you to change this turns per meter, and N is just going to be equal to turns. Okay, so this is going to be a capital N. Okay, and you're going to introduce one more thing here, and that is this, capital L, and this is going to be length of the solenoid. Okay, there's one other problem here that was produced when I went to print this, and that this P here should be pi, not a P. Probably looking at that and saying, what the heck is that? Pi. So one of the things that I don't like about this is that I don't like, every time I use this permeability of free space constant, I have to multiply 4 times pi. So in my own mind, I just went ahead and did a quick calculation to cut one corner every time I have to use it. And that is to do the multiplication and enter this value in my on my card. And so this turns out to be 12.57 times 10 to the minus 7 Tesla meters per amp. Okay, and so this is going to really simplify things. So the moment you've all been waiting for, what is the actual equation since we crossed this out? Here it is. The field strength produced by the solenoid is equal to the permeability of free space times the number of turns divided by the length of the solenoid times the current in amps, just like that. Okay? And so it's okay, well, why don't we give it a shot? Why don't we try to try it out? And so let's look at page 277. There is a quick check, and we'll do one of those, and then we'll come back to this page. And I think at the end of this page, yeah, the end of this page is going to be the end of the day. Okay, so 7.2, quick check, 7.2.2. This is on page, oh, here we go. Okay, so I'll snap this out, and I will show this to you. And it says here, this is the one we're doing here. Solenoid is 15 centimeters long and has 250 turns. What is the magnetic field strength inside of the solenoid if the current in the coils is 3.8 amps? Okay, so here we go. What do we know? We know that the length is equal to 15 centimeters. But you already know that you're not going to be using centimeters, you're going to be using meters, so this has to translate to 0.15 meters. Okay? So far so good. N is equal to turns, which is equal to 250. B is what we're looking for, and the current is equal to 3.8 amps. And we already know that what do they call it? I keep calling it the coefficient, but it's the permeability is, what did we say, 12.57 times 10 to the minus 7 Tesla meter per amp. Okay, so now let's plug it in, and we're looking, of course, for B. B is equal to so we just plug and play. Oh, so exciting. I'm not going to put the units in again. I'm running out of space. Times N, which is 250. Divided by the length, which is 0.15, and times 3.8, and so this all falls out at 8.0 times 10 to the negative 3 Tesla. Okay, so that is just how easy this is. The other questions in the quick check are basically the same. They'll give you maybe maybe it'll ask for the current and they'll give you everything else, but they're just variations of that one equation, and that's pretty much it for that. Okay. The last thing that I want to talk to you about today is on the bottom of page 5, and this is again this is where I started to go sideways on what talking about a couple minutes ago, the force and all that kind of stuff. So here, this is the equation that was kind of like bogging us down, or bogged me down. Didn't bog you down. But so suppose that we have this field, this magnetic field here, and here is a wire going through the magnetic field, and they're asking for what is the force. And so in order to just get a sense of where the force would go, again we're looking at the right-hand rule. So the right-hand rule says you point your thumb in the direction of the current. So here's I wish this was a bigger picture. So I putting my thumb in the direction of the current. I'm putting my fingers in the direction of the magnetic field, because it's going from north to south this way. And so coming out of my palm is where the force vector is. So in this case, the force is going in an upward direction. Okay, so that's what this is about. So that will give you a sense of what the directionality is, but this here is going to tell you how to calculate that. Now this is the basic formula that we looked at earlier on, and I don't want you to even look at it. If you want to look at it, go ahead. I'm not going to stop you, but this is our starting point, okay, for determining force and what, and given the charge, the velocity, and the strength, the magnetic field strength. Okay, ignore this, because all of this is just deriving this final guy here. This is the important one, and this is, I suggest what you do is, again on your card, maybe even do a doodle of this, and write down this. So what is all this about? So this is the force. This is the current in the wire. This is the length of the wire within the field. Length of wire. This, of course, is the field strength. And this is the angle, or sine of the angle, of the wire. So this is, because in this situation here, the wire is perpendicular, or it's 90 degrees to the what do you call it, the magnetic field. But what if it was going at an angle? Then everything changes now. It's going at an angle. So to find the direction, that's going to have an effect on the direction of the force. So if you have the wire at an angle, this will tell you which way this is going to change, because this is going to change this force. Okay, it's going to change it in some directionality. Okay, so this is angular direction. Okay, now it turns out that the textbook doesn't even give you any quick check for this. It just goes right into review 7.2. So I'm not going to spend a lot of time with you now. We're already at 35 minutes. So what I want you to do is, I don't want you to be spending a lot of time on this. My suggestion right now is to go back and do the remaining quick check questions. So do the quick check questions. You're not going to, like, these aren't going to be assessed, but I'd really like you to do those. Once you finish those, then maybe do 1 or 2 of the review 7.2, and then next day is going to be just doing 7.2. You're going to dedicate your time to finishing 7.2. I think there's 9 or 10 questions there, so I'm going to get you to do those, and you should have time left over next day. But what I'd like to do is just split it out into 2 days. Make sure you get a good basis for this, and then when we come back in 2 days hence, then we will move along to 7.3. Okay? So there will be another window for tomorrow, but it's just going to say work day. But bless you. I will see you in 2 days. I don't think I'm gonna. Yeah, see you in 2 days. Nah, maybe I'll do a little hello video tomorrow. Bless you. Love you. Go away.